So in this module, we're really going to start examining electronegativity and how this affects polarity within a bond. And we need to understand polarity because in the next chapter, we're going to talk about polarity as an overall to a molecule as well. So what is electronegativity? Electronegativity is defined as the measure of how strongly atoms attract bonding electrons to themselves. So it's looking at bonding electrons. Bonding electrons means they're shared between two atoms. How strongly can one of those atoms pull that bond towards itself? So it's an unequal sharing, or it results in an unequal sharing. This does follow your trends of ionization energy. So the higher the ionization energy, the higher the electronegativity. Remember what ionization energy is? Ionization energy is the amount of energy it requires to remove an electron from a gaseous atom or ion. How much energy do I have to pay to remove an electron? The higher your electron affinity, the more electronegative something is. So remember what electron affinity is? How much is an atom in the gaseous phase willing to pay for an electron? So that's why it follows the ionization energy trend as well. Ionization energy, how much energy do I have to pay it to give it up an electron? Electron affinity, how much is it willing to pay me to give an electron? If something really, really, really wants an electron, it's going to have a very high ionization energy because it doesn't want you to take them away. It wants more of them. If something really likes electrons, it's more electronegative. It's able to pull electron density to itself more. The difference between electronegativity and electron affinity. Electronegativity is a chemical property. It's showing how well an atom can actually attract electrons towards itself, but in a bonding pair. Electron affinity is the amount of energy released when an electron is added to a neutral atom. So this involves a transfer of electrons. This is just how much is it pulling a shared electron. So here's a nice chart of electron affinity. It's called the Pauling scale. I just Pauling went through and actually determined the electronegativity values of all the elements. And we can actually look at this and start to predict the type of bonds we're going to have based on their electronegativity. Sometimes you'll be giving these numbers, sometimes you will not. You still need to understand the trends even if you do not have these numbers. You need to know that fluorine is the most electronegative. Oxygen is number 2. Nitrogen and chlorine are tied for number 3. You need to know that the trend goes, it increases across and up the table. So what are the most electronegative elements? Well, fluorine wins. Your nonmetals are the most electronegative. Your nonmetals want electron density. The smaller they are, the more they want it. So why does nonmetals want them more? Well, because they can be more like a noble gas then. Why does the smaller atoms want them more than the larger? Because the smaller atoms are closer to the nucleus. Like you've got less things in between your outer electrons and your nucleus. The larger we go down that, or the farther down we go that table, those molecules get bigger and bigger, and they don't care as much because they can stabilize themselves other ways. The smaller atoms want these. They want the electrons. Least electronegative would be down here. Metals and low on the table. So again, if you're given the values themselves, you need to be able to understand what these values mean. It's a difference in these values. So like hydrogen is 2.1, carbon's 2.5. The difference between the electronegativities is what tells me what type of bond I actually have. But even if you're not given those numbers, you need to understand the trends and be able to make educated guesses based on what you know. So for HCl, for example, HCl is an acid when it's an aqueous form, but it's also a molecular compound as a gas. In HCl, chlorine is more electronegative than hydrogen. We know chlorine is tied for number 3. It's 3.0. On the Pauling scale, it's a 3.0. Hydrogen, 2.1. Do you have to know the numbers? No. You do have to know that chlorine is a lot more electronegative than hydrogen, though. What happens here is that the electrons spend more time around the chlorine. The chlorine, we draw this a few different ways. We can draw partial positive, partial negative. Partial positive meaning the hydrogen has a partial positive charge because it has less electron density. The chlorine has a partial negative charge because it has more electron density. We draw this arrow emphasizing which direction the dipole is going. We call it a dipole moment. Or we can draw it like this, showing that it's a larger electron density around the chlorine atom than around the hydrogen. So the bond itself is polar. This bond in between the hydrogen and chlorine is polar. Polar means that there's a large enough difference in electronegativity. Hydrogen is 2.1. The difference is 0.4. Say that this is non-polar, that neither atom is electronegative. With the difference in electronegativity between the bonded atoms, between the bonded atoms, 0.5 and 1.9, we call this polar covalent. We're still saying that they're sharing, but it's unequal now. More electronegative element. Pulls electrons more. And if the difference is greater than or equal to 2, it is ionic. Before this point, we have always told you, or I have always told you, that metal, non-metal is ionic. Not actually true. It does depend on the electronegativity. So we could have a metal, non-metal bond that is actually considered polar covalent, not ionic, because it actually depends on this difference in electronegativity. Remember, bonding character is a spectrum. It's a continuous spectrum. So it's about where do we fall on this spectrum to be able to tell if the compound is truly polar covalent or ionic. So just as a quick example here, we've got a ClCl bond, chlorine-chlorine. This is pure covalent. It is bonded to itself. The electronegativity of chlorine is 3.0. If it's bonded to itself, that means the other atom it's bonded to is also 3.0. So the difference in electronegativity is 0, and this is considered to be pure covalent. If I look at HCl, we already told you this is polar, but let's look at it again. We see that the electronegativity of chlorine is 3. The electronegativity of hydrogen is 2.1. That is a difference of 0.9, which is considered polar covalent. And sodium chloride, we know this is an ionic compound, and this further confirms that it is in fact an ionic compound. The electronegativity of chlorine is 3. Sodium is 1. Difference here is 2.1, or 2. I don't remember if sodium's 1 or 0.9 now. I need to check my notes. Check back on a previous slide. Let's see, what is it really? It is 0.9. That is a typo here for 1. So this should say 0.9. 2.1, and this is, in fact, yes, an ionic compound. So how do you apply this? Well, of the bonds shown below, which is the most polar? Carbon-carbon, carbon-nitrogen, carbon-oxygen, carbon-fluorine. Note, they're all bonded to carbon. So it's all about the difference with carbon. I'm not giving you numbers here, but you can still do it even without numbers because they're all bonded to the same thing. If they weren't bonded to the same thing, no, you couldn't quickly tell me the answer. Numbers would be helpful. But here, it's really, what about carbon-carbon? Well, this is pure covalent. Why? Because it's bonded to itself. Nitrogen, oxygen, fluorine. Regardless of what carbon is, I know fluorine is most electronegative. I know oxygen is second most electronegative, and nitrogen, tied with chlorine, is number 3. Which means that this will be the most polar bond because it's got the most electronegative element bonded to carbon. And this, I keep meaning to move. I don't know why I never do, but this is not the best place for this, but this goes back to the exceptions to octet rules. Why do these structures work best with less than octet? If I look at boron, BF3 forms a structure like this. AlCl3 and BeCl2. We told you guys when we looked at exceptions that boron and aluminum like to have 6 electrons or 3 bonds, and beryllium likes to have 2 bonds or 4 electrons. And it's exceptions to the octet rule. If you count up formal charge on these, every atom will have a formal charge of 0. Whether that be an outer atom or your central atom. Everything has a formal charge of 0, therefore this is the most stable they can be, which is why aluminum, boron, and beryllium don't like to have their octet, because this way they can keep their formal charge at 0.